Now let's begin with the next part of the chapter, that is hydrides. Now what are hydrides? These are the binary compounds of hydrogen with other elements. Metals can be there, non-metals can be there, except noble gases. So these are known as hydrides. Hydrides have the general composition EHX, where X can be any number. For example, we have learned MgH2, sodium hydride, etc. So many are there. Now these hydrides are classified into three main types. The first type is ionic or salt-like hydrides. The second type of hydride is molecular or covalent hydrides. And the third type is metallic or interstitial hydrides. Okay, so these are the three main types of hydrides. Now we'll discuss them one by one. Now the first type is ionic hydrides. These are also known as salt-like or saline hydrides. These are formed by combination of hydrogen with group first. Now group first means alkali metals, and group second. Group second means alkaline earth metals elements. Okay, and now we know that alkali metals as well as alkaline earth metals are highly electropositive. Okay, so S block members. So what are ionic hydrides? These are formed by the combination of hydrogen with S block elements. Now what are the examples? So we'll take some examples here. Suppose if I take lithium and this lithium is heated with hydrogen. Okay, so I will get lithium hydride. Suppose I am having calcium plus hydrogen. If it is heated, I will get calcium hydride. Okay, so alkali and alkaline earth metals, when they are heated with hydrogen at high temperature, they give the corresponding hydride. Okay, now we'll discuss the characteristics of ionic hydrides, that what is their nature. So now we are discussing the general characteristics of these hydrides. The first is these are white or grayish in color and are non-volatile in nature and are crystalline solids. Okay, they have salt-like structure. That's why they are also known as saline hydrides. The next is these have high melting point and boiling point. Okay, because they have crystalline structure, they have ionic bond, so the melting points and boiling points are very high. The next is these conduct electricity in molten state and liberate hydrogen gas at anode. Suppose I am having LiH. Now when current is passed, what will happen? It will dissociate into Li plus and H minus. Now we have anode which is positive and we have cathode which is negative. Now to the positive, H minus will move. Okay, it will lose electron here and H plus H will change to H2 gas. Likewise, at cathode reduction occurs and lithium is deposited. Okay, so because they dissociate into ions, okay, so in the molten state they conduct electricity. The next point is these are easily oxidized by air to form oxides. Okay, so these hydrides, when they are treated with oxygen, they form oxides. For example, I am having this hydride. Now it is treated with oxygen, so I will get oxide plus water. Okay, so these change to oxides on treatment with air. Likewise, these are hydrolyzed by water. Okay, so they also show hydrolysis reaction with water. Suppose I am having NaH. Now when it is treated with water, I will get NaOH plus hydrogen gas is evolved. Okay, a base is formed and along with base hydrogen gas is evolved. Okay, because of the formation of hydrogen gas, the reaction of these hydrides with water is very explosive. Okay, so generally we cannot extinguish this fire with water or with carbon dioxide. Okay, so this reaction is highly exothermic and it is highly explosive. Now, the next important point regarding these ionic hydrides is these are powerful reducing agents. Okay, so these can reduce the other elements. For example, in this reaction, you can see that carbon monoxide is reduced to carbon. So these hydrides also act as powerful reducing agents. And sometimes they are also used to prepare complex hydrides. For example, when NaH is treated with B2H6, okay, now what will happen? A complex compound is formed, that is NaBH4. This is sodium borohydride. Likewise, when LiH is treated with Al2Cl6, we'll get this compound, that is LiAlH4. This LiAlH4 is lithium aluminium hydride. Okay, so this is sodium borohydride and this is lithium aluminium hydride, and both NaBH4 and LiAlH4 are strong reducing agents in themselves. Okay, so these were the characteristics of ionic hydrides, and now we'll move to the next type of hydride, that is molecular or covalent hydrides. Now the second type of hydrides are molecular or covalent hydrides. Okay, now these are formed by the combination of hydrogen with p block elements. P block elements means electronegative elements from group number 13 to group number 17. Noble gases do not make any compound with hydrogen, so we are not mentioning group 18 here. Now we have well-known examples here. We know about these examples. HF we know, PH3, NH3, H2O, methane, CH4. Okay, so these are the examples of such type of hydrides. Okay, now these molecular hydrides are further classified depending upon the number of bonds and electrons in their Lewis structures. So if we make the Lewis structures of these hydrides, so depending upon the number of electrons, these are further classified into three types. The first type is electron deficient, the second is electron precise, and the third is electron rich. Now what are electron deficient hydrides? These are formed by group 13 elements. Boron, aluminium. These have less electrons for writing Lewis structure. Okay, now group 13 elements have only 3 electrons in the valence shell. So they will be making only 3 bonds. So definitely the octet is incomplete. That's why they are known as electron deficient. And what happens? Suppose my molecule is BH3. Now BH3 is unstable because the octet is incomplete. So what this boron will do? It will dimerize. So the final structure that we'll get is B2H6, and this B2H6 is known as diborane. Okay. So such type of hydrides, since they have less electrons, octet is not complete, so in order to get stable they polymerize or they dimerize. The next is electron precise. These are formed by group 14 members and these have sufficient number of electrons as required for writing the Lewis structures, means the octet is complete. Now group 14 means carbon silicon, so we have CH4, we know it is methane, SiH4, it is known as silane. Okay, and the last is electron rich. Now these are formed by group 15 to group 17 members. Now what happens in these? These have excess electrons which are present as lone pairs. So after writing the Lewis structure, what we'll find? We'll find some extra electrons. And these extra electrons are represented as lone pairs. For example, in NH3, nitrogen is having one lone pair. In water, oxygen is having two lone pairs. And in HF, fluorine is having three lone pairs. Okay, so and because of the presence of lone pairs on the electronegative elements, these are also involved in the formation of hydrogen bonding. Okay, this we have discussed in chapter number 4. Okay, so these molecules NH3, H2O, HF, these are involved in the formation of hydrogen bonding, intermolecular hydrogen bonding, which is responsible for very high boiling point of these electron rich hydrides. Okay, so these are the types of molecular hydrides. Now we'll discuss the general characteristics of molecular hydrides. Now the first characteristic is these hydrides are soft. These have low melting point and boiling point, and these are volatile in nature. And the reason why they are volatile in nature, it means the intermolecular force of attraction is weak. And what is the weak intermolecular attraction? It is weak van der Waals force of attraction. So in between the molecules of these molecular hydrides, only van der Waals force of attraction is there. That's why they are volatile. Okay, and this van der Waals force of attraction is sometimes known as hydrogen bonding. Okay, suppose I have water. So water makes intermolecular hydrogen bonding. Okay, so hydrogen bond is also a type of van der Waals force only. And since they have covalent bonding, okay, no ions are there, so these have low electrical conductivity. So this is all about the second type of hydride. The third type is metallic or interstitial hydrides. Now we'll discuss why these are known as interstitial hydrides. These are formed by D and F block elements. Okay, now D block we have groups 3 to 12. So group number 3, 4 and 5 will easily make hydrides. In group number 6, only chromium makes hydrides. Group number 7 and 8 do not make any kind of hydrides. This is known as hydride gap. So 3, 4, 5, 6 are making hydrides. They are combining with hydrogen. 7, 8 and 9 members do not combine with hydrogen, and afterwards the rest groups 10, 11 and 12 also combine. The examples are scandium hydride, ytterbium hydrides and so on. F block elements, lanthanoids and actinoids also combine with hydrogen to form hydrides. Now these hydrides are prepared by directly adsorbing the hydrogen into the lattice of D and F block elements. Now what is the meaning of this lattice? Lattice means regular 3D arrangement. Since D and F block elements are solids, so they form a regular arrangement. Now this regular 3D arrangement is known as lattice. Now in the lattice we can see some vacant spaces are there. Now in these vacant spaces we can trap this hydrogen. Okay, now these vacant spaces are known as interstitial space. Okay, so in these hydrides, metallic hydrides, what happens actually, the hydrogen is directly adsorbed into the lattice. So hydrogen occupies the vacant space or the interstitial space. That's why these hydrides are known as interstitial hydrides. Okay, now what will happen? All the vacant spaces are not filled. Suppose we have 100 vacant spaces. Now out of 100 vacant spaces, suppose only 30 are filled with hydrogen. Okay, such compounds which do not have a same ratio of cation and anion, they are known as non-stoichiometric. So these hydrides are non-stoichiometric in nature. Now, what is the meaning of non-stoichiometric? Non-stoichiometric means the ratio of cation and anion is not same as indicated by their formula. For example, we have titanium hydride. Now, X can be 1.5 to 1.8. Okay, so with one atom of titanium, I can have 1.5 to 1.8 atoms of hydrogen. Such compounds are known as non-stoichiometric, means the ratio is not whole number. Stoichiometric means the ratio is whole number. For example, sodium chloride, NaCl, 1:1 ratio. Okay, so these hydrides have hydrogen which is trapped in the interstitial space. Here the hydrogen is not making any kind of bond. It is simply trapped. Okay, so these hydrides are non-stoichiometric in nature. Now the general characteristics are, these are hard, these have metallic luster, and these conduct electricity. These are non-stoichiometric, this point we have discussed earlier. Now these give out hydrogen readily, so they are strong reducing agents. So these hydrides, when they are heated, they readily give out the hydrogen. Now hydrogen there is present in the atomic state. That's why they can be used as a reducing agent. And since in the metallic hydrides we are trapping hydrogen, so this can be used for hydrogen storage. It is not possible to store hydrogen in a cylinder because it is highly explosive. So what we can do, how to transport hydrogen from one place to another. So this is an option for hydrogen storage. Okay, so this was all about your hydrides, that is ionic, molecular and metallic hydrides. Now let's move on to the next part, that is the compounds of hydrogen. And the first compound of hydrogen is water. We all know about water. Okay. Now water is an essential to all the forms of life. We can live without food for some days, but we cannot live without water. Okay. Our body is our body contains 65% water. Okay. And water is a universal solvent, means it can dissolve a variety of compounds. And one of the most important property of water is that it can be changed from solid to liquid and liquid to gas state. Okay. It is the principal constituent of our earth surface. So water has unique properties. So now we are going to discuss some important physical and chemical properties of water. Now before that, we'll discuss the structure of water. Now, what is the structure of water? We have learnt in chapter number 4 that water has central oxygen atom. Now, this oxygen is bonded to two hydrogen atoms, and this oxygen is having two lone pairs. The bond angle is 104 degree. Now, since oxygen is having two bond pairs and two lone pairs, the hybridization is sp3. And what is the shape of water? It is bent or angular shape. Okay. So this is the structure of water. Now, since the oxygen is more electronegative in nature, so suppose this is oxygen. Now we can make the dipole moment vectors. Okay. So the vectors will be up, and because of this, water is a polar molecule. Okay. Water has a resultant polarity. It has a resultant dipole moment of 1.84 d. Okay. So water is a polar molecule because oxygen is more electronegative as compared to hydrogen. Okay. And because of this electronegativity difference, water can also make hydrogen bonding. Okay. So water shows intermolecular H bonding. Okay. And this intermolecular H bonding is like this. Now this is del plus, this is del plus, this is 2 del minus. So one oxygen atom can make two hydrogen bonds like this. Okay. So because of the electronegativity difference, water can form hydrogen bonding intermolecular hydrogen bonds. Okay. And this intermolecular hydrogen bonding is present in liquid state as well as in the solid state of water. And what is the solid state of water? That is ice. Now we'll discuss hydrogen bonding in water and ice. In water, in liquid state, the water molecules are held by hydrogen bonds in 3D network. So you can see a 3D network is there. So each oxygen is making two types of bonds. Two are normal covalent bonds and these two are hydrogen bonds. Okay. But what happens when water is changed to ice? Now ice means it is the solid state of water. Now the molecules are freezed here. So the molecules will not move. What happens in liquid state? The molecules are in constant motion. So what happens when the molecules are in constant motion? The hydrogen bond break, again it is formed, then it breaks, again it is formed. So it is continuous forming and dissociation of hydrogen bonds. But in ice, that is in solid state, the molecules cannot move. So hydrogen bonds are fixed. So you can see that each oxygen atom is making four types of bonds. Two are normal covalent bonds and two are hydrogen bonds. And these hydrogen bonds are not collapsing. Okay, they are in the fixed position. And because of this, there is lot of vacant space in the structure of ice. And this vacant space is filled with air. And because of this air, the density of ice is less. Okay, that's why ice floats on surface of water. Okay, so what is the reason that ice is lighter than water or the density of ice is less than water? Because in ice, the hydrogen bonds are fixed now. The molecules are fixed now. Okay, and because of this, so many vacant spaces are there in the structure of ice, which are filled with air. So, ice floats on the surface of water. Okay, and this property this property is quite helpful for the survival of aquatic organisms also, because what happens in winter season, the upper part of the lake or any river freezes. So what will happen, since ice is lighter than water, so it will float on the surface of water. So the water which is below the ice, okay, that is having a temperature which is more than 0 degrees Celsius. So it enables the aquatic organisms to withstand the winter. Okay, so this ice basically provides insulation for the aquatic life which is present in the water below it. Okay, so this property is quite helpful for the survival of aquatic organisms. So in severe winter, the upper layer of water freezes and does not sink to the bottom because ice is less dense than water, and it provides thermal insulation for the aquatic life in the water below it. Okay, now we are discussing the physical properties of water. The first physical property of water is liquid at room temperature. And what is the freezing point of water? The freezing point of water is 273.2 Kelvin, and what is the boiling point of water? It is 373.2 Kelvin. The second is water is having a density of, this is the maximum density of water, 1 gram per centimeter cube at 4 degrees Celsius. So the maximum density of water is 1 gram per centimeter cube at 4 degrees Celsius. Okay. The next is, it is polar in nature because of the high electronegativity of oxygen. Water has a resultant polarity, and since water can dissolve many organic compounds, it is a universal solvent for majority of the ionic as well as the covalent molecules. So these are the important physical properties of water. Now we'll discuss the chemical properties of water. The first property is water is quite a stable compound. Okay, it does not dissociate into its elements readily. But when the temperature is more than 1500 Kelvin, or when we pass electric current, it can dissociate into its constituent elements, that is hydrogen and oxygen. So twice H2O will dissociate into hydrogen and oxygen at a temperature greater than 1500 Kelvin, or when we pass current either in the presence of small quantity of acid or base, because pure water is bad conductor of electricity. Okay, so water into the water will add few drops of acid or base, and then it will dissociate into its constituent elements. So this is the first property of water. The second property of water is amphoteric nature. Okay, water is amphoteric in nature, means water shows acid as well as base. The next is water shows amphoteric nature, that is it shows acidic as well as basic nature. It behaves as an acid as well as base, because water has tendency to give H plus ion as well as OH minus. Okay, so it can act as an acid as well as a base. But pure water has a pH of 7, and pure water is neutral to litmus. So water can act as a base. Now here water is treated with HCl. Now HCl is more acidic as compared to water. So here it is acting as a base. It is combining with acid. Okay, and water can act as an acid also towards the bases like NH3. So water can react with acid also as well as with base also. And water ionizes on its own to form H3O plus. This H3O plus is known as hydronium ion, and OH minus ion. And this self-ionization of water is known as autoprotolysis. So we can see that water is amphoteric in nature. Now next important chemical property of water is regarding its oxidizing as well as reducing character. Water behaves as oxidizing agent as well as reducing agent. So when it is working as an oxidizing agent, okay, so what will happen? Suppose this is water. Now it is treated with more electropositive metal. Okay, sodium is more electropositive. So what will happen? This sodium will reduce this water to hydrogen and will get this compound. Okay, so here water is reduced. Here reduction is taking place, and reduction is taking place means water is acting as an oxidizing agent. So water can be reduced by the metals which are more electropositive than hydrogen, and in that case water will act as an oxidizing agent. And as reducing agent, okay, reducing agent means itself it is oxidized. So water is oxidized by more electronegative elements. Okay, so here this water is oxidized, and since water is oxidized to O2, so water here it is working as a reducing agent. So water combines with electropositive as well as electronegative elements. When it is combining with electropositive elements, it works as an oxidizing agent, and when it is combining with electronegative elements, it works as a reducing agent. Now the next most important reaction of water is hydrolysis reaction. We know that water can hydrolyze many ionic and covalent compounds. Water has unique, strong solvating power because of its high dielectric constant. Water is an excellent solvent. It can dissolve many compounds, ionic compounds, covalent compounds. Now these are the reactions. Okay, water can dissolve many compounds. It reacts with many compounds, many types of compounds. So these are the hydrolysis reactions. The next reaction of water is hydration reaction. Now hydrolysis is different than hydration. In hydrolysis, water reacts with the compound and a new product is formed. But in hydration, what happens? Water can form hydrates with some metal salts. Here, water can be present in the voids. Voids means vacant space in the lattice, or it is hydrogen bonded. We all know about copper sulfate, CuSO4.5H2O. Okay, now in copper sulfate, what happens? There are 5 water molecules. Out of the 5 water molecules, 4 are hydrogen bonded to copper, and the last or the 5th water is hydrogen bonded to sulfate. So here water is not making a new product. Basically, water is linked to the structure. Water is present in the structure, and because of this water, the physical state of the salt is not changed. CuSO4.5H2O is solid in nature. In barium chloride, now 2H2O are there, and these water molecules are present in the vacant space in the lattice. So these are few important chemical properties of water.